Let's take a look at the structure of the atom in light of quantum mechanics and connect that with the periodic table as we know it today. Dmitri Mendeleev was the man who came out with the first successful periodic table. I say it's a theory that was 50 years ahead of its time because Mendeleev knew nothing about atomic structure. He had no knowledge of protons or electrons or certainly neutrons. He knew none of the noble gases. He was missing several dozen elements in his list of elements in atomic masses. And yet Mendeleev came up with a theory that gave us a usable periodic table that showed us elements that were like each other. Here's Mendeleev's periodic table as published in German scientific literature. And you can see it looks a lot like the one we use today. Here's group 1, hydrogen, lithium, potassium, rubidium, and cesium. He also has sodium here, but he has copper, which has a +1 valence, and a silver also has a +1 valence. We know that they are not alkalis, however. Here's a lot of the group 2 elements that we're familiar with: beryllium, magnesium, calcium, and the halogens, fluorine, chlorine, bromine, and iodine, are also here. So there's a lot of the elements that we are familiar with. You'll notice something about his table in just a moment. Now, Mendeleev said as atomic mass increases, the element's chemical properties recur periodically. So beryllium and magnesium are in the same column. They both react with hot water, very hot water, and they form compounds with chlorine in the ratio 1:2. Fluorine, chlorine, bromine, and iodine are all reactive nonmetals, and they combine in similar proportions with the same metals. So for instance, sodium chloride is NaCl, sodium bromide NaBr, sodium iodide NaI. On the other side of the table, sodium, potassium, and lithium are all soft metals that react with air, oxygen, and water similarly, and they form compounds like NaCl, KCl, LiCl. The thing that made Mendeleev's table most exciting to chemists is that he left gaps where he thought elements were yet to be discovered, that there was nothing in that atomic mass range that had properties similar to the elements above and below it. Columns of the periodic table represent families with similar chemical properties. Moseley came along about a half century later and discovered that the periodicity depends not on the atomic mass but on the atomic number of elements. And he was able to very cleverly measure the number of protons in the nucleus. The nucleus had only recently been discovered, and the atomic number is the number of protons. Also in a neutral element, the number of protons and electrons are the same. Moseley, however, knew the inert or noble gases. He called that group 0 here, and so he generated the periodic table in its basic modern form. Here is the modern periodic table. I've ignored the lanthanides and the actinides. Rows are called periods. Columns are called families or groups. Now, let's go to the wave mechanical model. The electron that makes an atom special is the one that gives it its chemistry. See, each element has all the electrons of the elements before it, plus one more that makes it unique. Let's look at hydrogen. Hydrogen's unique because it's the only one with just one electron and one proton. It is the most common element in the universe. We know that from spectral data. Hydrogen really doesn't belong with any other group in the periodic table because it is unlike all other elements. Even though we list it with group 1 because it has a valence of +1, it really doesn't belong with the alkalis. It's not a metal, it's a gas. It doesn't form ions, it forms molecules. All the alkalis are different. And as a gas, it comes in packages of 2. We're familiar with the formula H2. It is a diatomic gas. Hydrogen does not give away its electron like the alkalis. It shares its electron in what we'll call a covalent bond. Hydrogen's electron configuration, you're probably aware, is 1s1. You can see that it has a single electron, and that's in an s orbital. It's also seen sometimes in an orbital box configuration with an arrow that represents the electron spin. That's like this. So this is a representation of hydrogen. We would draw usually a 1s next to the box. Now helium is the second most abundant element in the universe and is characterized, its special electron is also a 1s. So it has the 1s that we're familiar with from hydrogen, and it has its own 1s. Therefore its configuration is 1s2. It also may be represented with the box and the arrows. In this case, there will be 2 electrons with opposite spins. Now we move to the rest of the periodic table, and we recall that as we move from element to element in the table, each element has all the electrons of the element just prior, and then it has its characteristic electron determined by its row and column. We're back to group 1A, or group 1. It loses 1 electron easily. It's characterized by a single s electron. The energy level of the electron is the same as the period. S1, P0. There are no p electrons on the first energy level. There are on the second and third and others. So lithium has all the electrons of the previous element helium, which is 1s2, and it's characterized by a single s electron. So we write 1s2, 2s1. And there's your boxes. That makes lithium very easy to attack. We'll see that the helium core of 2 electrons is low energy and stable. The 2s electron here, however, is fairly easy to lose. It has a low ionization energy. Now we have a shortcut for all the elements that have a noble gas somewhere in front of them. Since the noble gas core of every element does not react, we can show every element like this. The noble gas core, in this case helium, along with the characteristic electrons of the next energy level. Group 2A, or 2, loses 2 electrons easily. It's characterized by 2s electrons, and its period is equal to its energy level. And so here with beryllium, we have a 2s2 characteristic electron. And there are your boxes. Now the 2s orbital has been filled, but there are still 3 2p orbitals to fill. Remember, on the second energy level there are 4 orbitals in all, 1s and 3 p's. Group 3a is generally shiny metals. They lose 3 electrons. It's characterized by 2 s electrons and 1 p electron. So boron element 5 has all the electrons of beryllium plus a p electron. And we say it's 1s2, 2s2, 2p1. Showing boron with orbital boxes, we show all the equivalent p orbitals. 2 of them are completely empty, and 1 is half filled. Moving to the carbon family, these bond covalently, except right down here with tin and lead. which can form ionic bonds. These have 4 electrons to share. So what would be the electron configuration of carbon? To have all the electrons of boron plus 1 more, and that would be a 2p electron. So carbon, 1s2, 2s2, 2p2. And there is the boxes. Hund's rule tells us that the equivalent orbitals, 1, 2, 3 orbitals, half fill before they completely fill. In group 5a, the nitrogen family, we have covalently bonded atoms, and there are 3 electrons that can be shared, because one of the p orbitals, none of the p orbitals are completely empty. All of them are half filled, and so S2p3 is what we find in this column. The group 6a are the oxygen family. They're characterized by S2p4, 1, 2, 3, 4. These can either gain 2 electrons and become ions, -2 ions, or they can share, as they do in water. In group 7a, the halogens are characterized by S2p5. They tend to gain 1 electron and become a negatively charged ion, and in that way they attain a noble gas configuration of S2p6. Group 8a, the noble gases, once called inert, all have an S2p6 configuration. They are all low energy and they are all quite stable. There are 40 metals placed between the group 2 and group 13, and they're called transition metals. They're often called B elements on some periodic tables. In periods 4 and 5, the d orbitals half fill and then they completely fill. Remember, in period 4, unless we get to calcium, we now still have to fill the 3d orbitals, and so those are the ones that fill from scandium through zinc. The d orbital in the 3rd energy level is very close to the s orbital in energy, the 4s orbital in energy. So we can see from time to time some borrowing going on. Copper can borrow a 4s electron and drop it into 3d orbital and lose 1 electron to form Cu2+. Or it can lose the last d electron and form Cu2+. Zinc has a full set of d orbitals, so the only electrons it ever loses are the ones in the 4s orbital. Zinc 2+ is the only low energy stable ion of zinc. Transition elements often form colored salts in water, and this is a quantum effect of coordination chemistry. You'll study this in little depth in AP chemistry. Then the inner transition elements form by adding electrons to f orbitals. Remember, each table group, up and down, has elements that react similarly, and as you move from left to right in a period, chemical properties start off metallic, and by group 7 are non-metallic. And very importantly, the noble gases, helium through xenon, and even radon, they don't react at all under normal circumstances.